Okay, so as I mentioned, we've got a expression now we've got a constraint here that involves ct, little kt plus 1, and lt. So here you see that the planner is maximizing over these three variables. Let's make this problem a little simpler. Let's substitute out the little ct consumption per worker. So we're going to replace this guy with this expression over here. All right, so we've done that down here, as you can see. So this is our new problem, and it's only in terms of the LTs and the KTs. Now, of course, you have to remember that LT is a whole set of LTs, and KT is a whole set of KTs. Okay, so this is T equals, oh, why did I put two crosses? T goes from 0 to infinity, right? So the reason why the planner only has to choose kt plus 1 is because technically little k0 is given. That's a constraint of the problem. Initial capital stock per worker is given in the problem. But in any case, this is what we're going to do. So once we've got the problem this way, we have an unconstrained optimization problem in two variables. That's going to be possible for us to solve because you can see here that LT is entering positively here and negatively there. So that there's going to be this trade-off between working more and having more leisure. All right. So that's one thing. The second thing is you'll notice here that we have a KT here and a KT plus 1. So for instance, in hold on one second. Ignore that. That Slack channel. Sorry. Anyway, so let's see here. Where was I? Right, so we've got a capital entering here with the positive sign and capital entering here with the negative sign. And if you think, so, capital in period 1, say, is going to appear twice because it's going to appear once in period, when we're like summing over period 0 here, we're going to have t plus 1 here. So that's going to be like period 1 is going to be here. And then when we iterate down here to period 1, then k1 is going to be here. So we're going to have k1 enter once with a negative sign and once with a positive sign. So again, we can sort of do this maximization in an unconstrained way because we have the capital entering with both a positive and a negative sign. So labor enters with a positive or negative sign, capital enters with a positive or negative sign. The big difference is that you see labor is, it always has a subscript t, right? So we can just kind of look at that period by period, whereas capital we have to think about two periods, this period and next period. All right, so that's going to be kind of the theme of the next slide. This is kind of just, so this is just copied from the last slide. And then you can see I'm just writing what I just said here. Okay, so if we're optimizing with respect to kt plus 1, it's going to enter in two periods. It's going to enter once in a period. So I mean, suppose that we're taking the derivative with respect to period 1. Well, then once period 1 is going to come in here as 1 plus r. So we're going to have a 1 plus r term here. That's this part. Right, and then once we're going to have it coming in here as this t plus 1 term. So that's what we see here. All right, and then the reason you'll notice we have this uct term here and uct plus 1 here. So by uc, what I mean is the derivative of u with respect to c. Okay, so the derivative of this term with respect to c. Okay, so anyway, our first order optimization, our condition is going to be to set this thing equal to 0. All right, and then using the same trick we did before, noting that nt plus 1 divided by h is just e to the power n times nt divided by h, right? We can multiply the numerator and denominator by nt. Then we're going to have, this thing here is going to turn into an nt. We're going to have an nt there. We can cancel those out. So in other words, we can cross that out, and then write in an e to the power n here. All right. We're going to be able to solve for this expression here. Let's see here. Right, so here we've got a e to the power negative rho t. Here we've got an e to the power negative rho t plus 1. So we can actually cancel out this term and then cancel out the t here. All right. Also, we've got an e to the power n here. Let me change my color maybe. Maybe I should have changed my color, crossing all this stuff out. Let me just do that. So I'll write in the e to the power n here. Then let me just start crossing out here with red. All right, so we argued that we can cross, well, this is now gone because we put in this e to the power n. All right, so we can cross out this, cross out that, that's gone. This is going to go away, and then here we're going to eliminate the t, all right? And then here we've got an e to the power n. That goes away because we can divide both sides by e to the power n. Anything else? Nope, I think that's it. So we have the negative UCT term left over here. We have e to the power negative rho times 1, right? So e to the power negative rho, 1 plus RT plus 1, and then UCT plus 1. So we end up with this expression, these two guys. And what we're probably going to do on the next slide is we're just going to rearrange so we can write UCT plus 1 divided by UCT is equal to well, before I actually write this down, let's just see how I do on the next slide. So, I mean, it's just this equation we can manipulate in various ways. I just don't want to do it a different way than whatever's on the next slide, which would be confusing. Oh, I see, okay. So let me just repeat from this last, let's see if I can do this again. This time I can't quite make it. Let me just rewrite this here. Negative UCT plus e to the power negative rho, 1 plus RT plus 1, UCT plus 1 is equal to 0. All right, so we can plug in log linear utility into this expression here. So notice if we have log linear utility where, well, it looks like this. So you can see that it's going to be the log of CT. So you guys remember that log looks like this. This is, oops. Yeah, that's right. So then the log of C would look like this. Okay. So we're going to have the log of that. We're going to have the log of leisure, the same thing. And then we have this parameter B, which is going to govern sort of the weight that people give to leisure versus consumption. If B is less than 1, then people prefer, well, you know, it depends on the units, I guess, but people prefer consumption to leisure. If B is greater than 1, they prefer leisure to consumption. I mean, I guess what's important is that the higher B is, the more people care about leisure relative to consumption. Okay. Yeah, so suppose we have this, then what is the derivative of U with respect to C, T? Well, that's going to be equal to 1 divided by CT. See, that's what the nice property here is that there's no C's here, so this term drops out. So, using this expression, let's see here, we're going to have UCT replaced by 1 divided by CT. We're also putting this on the other side here, right? And then e to the power negative p, 1 plus RT plus 1, and then 1 divided by CT plus 1. Okay. Because, yeah, exactly. All right, now you'll notice that we put in this expectation. Why do we have an expectation here? Well, let me actually go up here and take a look at this. So you can see that there was an expectation here, which actually we dropped down here. So we actually should have had an expectation down here. We should have retained it here as well. But in any case, I think I'm actually going to update that slide. So we have this expectation. You might say also, why is it ET? Why isn't it E0? It's because this is going to be optimizing starting at time t. So at time t, you actually know what happened. You know what your consumption is at time t for sure. Once you've chosen it, you know what it's going to be for sure. But you don't know what your consumption is going to be at time t plus 1 because it depends on the stochastic evolution of productivity and potentially government purchases that you can't fully predict. Okay, and you also can't predict the interest rate because of the same thing. You don't know exactly what production is going to be at time t plus 1. So, depending on shocks to this technology parameter, you might have different rates of return, which is going to give you a different rates of return. You might have different, I should say, you might have different rental rates, which is going to give you different rates of return. All right, so what's important here is actually that you can't separate these two shocks, consumption and the rate of return. Why is that? It's because they're probably correlated. So imagine that we get a very, very good productivity shock. So, utility is log, right? So the substitution and income effects are going to cancel out. So it's just going to make us richer. It's going to make us probably consume more at time t plus 1. So what that does, it's going to raise this thing, and since firms are more productive, they're probably going to want to rent capital more, which is going to cause RT plus 1 to go up as well. So when RT plus 1 is high, CT plus 1 is high as well. Hard to say exactly what's going to happen here, which direction this is going to go, but the point is they're probably correlated. They might be negatively correlated. They might be positively correlated. It's not clear exactly which ex ante. I think it depends on income and substitution effects, basically. Okay, so that's so that's an expression that comes out of optimization for capital. What about optimization for labor? Well, that's going to be a little bit easier because we only have t terms, so we'd only have to think about one period at a time. If we have, so without thinking about a particular utility function, we can just maximize, and you'll see that here we're going to have, basically the marginal utility of consumption times the wage, and then the marginal utility of leisure times nothing, because it's just negative LT here. So set those two guys equal to 0, and then using our log utility, we can just derive 1 over CT times WT is equal to 1 over 1 minus LT. That's it. Excuse me, not 1. There's a B there. It's a B. 1 minus LT is here. I got it down here. So we get this expression. Just rearranging a little bit, you can get, why rewrite it? It's right here. So, take that CT, put it over here, multiply both sides by CT, take the B, divide both sides by B, and you get the period relationship between consumption and leisure. And what you see is this totally makes sense. If the wage is higher, you're going to consume less leisure, all else equal. If B is higher, if I care about leisure more, then all else equal, I'm going to consume more leisure. So, this is kind of an intuitive expression. So anyway, here we have an expression that has a CT and an LT in it. Up here we have an expression that has a CT and a CT plus 1 in it. Hopefully that's enough for us to start thinking about the solution of this model. So let me stop there and start a new video.